Greetings and welcome to GILFORD'S lectures. So today we are going to be looking at the Part 2 solution to Nahpi Physics 2021-2022 academic year. Remember that the Part 1 has already been uploaded and is on the channel. If you have not yet watched the Part 1, then endeavor to do so. Also remember to subscribe to the channel because the Part 3 solutions will be uploaded very soon. When you do subscribe, turn on your notification bell so that you'll be the very first person who will be notified when the solutions have been uploaded. So question 11 of the question paper reads: an electron is traveling at right angles to a uniform magnetic field of flux density 1.2 milli-Tesla with a speed of 8 times 10 to the power 6 meter per second. The radius of circular path followed by the electron is A, B, C or D. So you are given options A, B, C and options D. We know very well that the magnetic force Fb acting on a charged particle is given by B cure V sine theta. But in the question we're told that the electron is traveling at right angles to the magnetic field and hence theta is equals to 90 degrees, and that reduces Fb to B cure V. Remember that B is a magnetic field strength, cure is the charge of the particle, and V is the velocity of the charged particle. Also, we're talking about a single electron. Therefore, from the formula, cure equals Ne, N is equals to 1, and hence cure is equals to E. This reduces Fb. This reduces Fb to be B E V. So let us now look at our solution. So when an electron is traveling in a magnetic field, if this is a magnetic field, if this is your magnetic field given to you, and an electron is traveling at right angles to this magnetic field, then it is going to assume a circular path. In this circular path, there is always a centripetal force, which is provided by the magnetic force BeV, where V is the velocity of the particle. Essentially, the centripetal force mv squared on r is equals to BeV. If we make r subject of formula, we are going to obtain mv on Be. And if you replace m by the mass of the electron, which is 9.1 times 10 to the negative 31 kilogram, and V by the value we're given in the question, and replace our B by 1.2 milli-Tesla, and our E by 1.6 times 10 to the negative 19 coulomb, we are going to obtain R, the radius, to be equal to 3.8 centimeter. Hence, the option A is the correct option. So now let us look at question 12, which reads: the gravitational field strength at the Earth's surface is approximately 10 Newton per kilogram, and the radius of the Earth is about 6.4 times 10 to the power 6 meter. The mass of the Earth is about, you are given options A, B, C, and D. So let us look at the solution. If you have the Earth, let us consider that sphere to be the Earth with mass ME, and you have a body of mass M placed on the Earth's surface, then there's a force of attraction. There's always a force of attraction. So there's a force of attraction between these two masses, and that force of attraction is the gravitational force of attraction F that acts between every two bodies in the universe, and is given by GME little m all over radius of the earth squared. So this is the force of attraction acting between the earth and the mass m. Also notice that when that object is placed on the earth's surface, so this is the object of mass m, then the weight of the object is given by mg and always act vertically downward and point towards the center of the earth. So now let us look at our solution. So F is equals to GMEm all over RE squared. This is the gravitational force of attraction between the earth and the mass, where the distance between the center of the earth and the center of the object of mass m is given by the radius of the earth. It therefore means that that object is on the surface of the earth. So the weight F is given by mg and you equate it to this quantity GMEm all over RE squared, making G subject the formula by cancelling out m. So here notice that m and m cancels out and you obtain G to be GME on RE squared. The aim was to obtain the mass of the earth ME, so this is the quantity we're interested in. So if we make this quantity subject of formula by first of all cross multiplying, so observe here that we have just cross multiplied. So when we do cross multiply and make ME subject of formula, we obtain G radius of the earth squared on G, that is little g, which is the acceleration due to gravity, and it was given in the equation as 10 Newton per kilogram, radius of the earth squared on G, where this capital G is the universal gravitational constant and its numerical value is 6.67 times 10 to the negative 11. Point your answer, you are going to obtain 6.1 times 10 to the 24 kilogram. Hence the option A is the correct option, and that is the mass of the earth. It is very important for you to memorize this value, because someone who already knows this value, when he just enters into examination hall and sees such equation, he just picks his answer directly and saves time for himself. So now let us look at question 13, which reads, an open-ended U-tube of uniform cross-sectional area contains water of density 1 gram per cm cube, standing initially 20 centimeters from the bottom in each arm. An immiscible liquid of density 4 gram per cm cube is added to one arm until a layer 5 cm high forms, as shown in the figure 3. What is the ratio H2 to H1 of the height of the liquid in the two arms? You are given options A, B, C, and D. So this is the figure, and this figure was labeled figure 3 in the question paper. So you are asked to get the ratio of this H2 to this H1 after addition of an immiscible liquid, which tends to consume a distance of 5 centimeters in this U-tube. So at this level, you are going to be observing exactly what happens when the immiscible liquid has been added into the U-tube containing the water. So let us start by considering this as our bottom line, where the U-tube sits on, and this is our U-tube containing water. Observe that the minuscule of the water is at this point, and this is the division line between the left and the right arms. So the distance from the point where the bottom line and the division line meet to the minuscule of the water on one arm was given by 20 centimeters, and on the other arm was also given by 20 centimeters. So we notice that when we add the immiscible liquid, then the immiscible liquid, so let's consider it to be this red liquid, it tends to press down the water, and the water is being lowered in one arm, that is the left arm, and is raised in the right arm. Now we look at, we now have a new minuscule, that is for this second line we have a new minuscule. So let us observe how we are going to use this information in the next slide. So now let us calculate the total distance occupied by the water in the U-tube. So we notice that from the point of intersection between the bottom line and the division line to the minuscule of the water on the left arm of the U-tube, that is on this left arm of the U-tube, the distance from this point to this point is 20 centimeters, and the distance from this point to this point also is 20 centimeters. Therefore, you notice that before the immiscible liquid was added, the water in both arms of the U-tube stood at 20 centimeters from the bottom. Essentially, 20 plus 20 equals 40 centimeters is the total length of water in the U-tube. So the total length of water in this U-tube is 40 centimeters simply by taking 20 plus 20. So now let us observe keenly what happens when we add the immiscible liquid in the U-tube. So when we add the immiscible liquid, remember that this red section of the U-tube is the immiscible liquid. So when we add the immiscible liquid into the U-tube, we notice that it presses down on the water in one arm and causes it to rise in the other. The distance occupied by the immiscible liquid when added is 5 centimeters, while the water still occupies 40 centimeters. So if this is our division line between both arms, then we are now going to call this distance h1 and call this distance h2 as we were given in the question. So we notice that the total distance h2 plus h1 is the sum of 40 and 5, as you can see here. So h1 plus h2 is therefore equals to 40 plus 5, which is equals to 45 centimeters. So you notice that when the immiscible liquid is added, that is the red layer, the water in both arms occupy a total distance of h1 plus h2 equals 45. So this plus this is equals to all of this. And we call this our equation 1. So we are also going to derive another equation using the hydrostatic law, and we are going to use those two equations to solve for h1 and h2 and later on the ratio. So at this level, we are going to be deriving our second equation. But before doing that, let us first of all do some analysis on the U-tube. Remember that this distance was the distance h1, while this distance was the distance h2. Also remember that this was a division line. So this is the line dividing both arms, and this distance was given by 5 centimeters. That is the distance occupied by the immiscible liquid. Remember that the immiscible liquid is this red section. Therefore, if you want to obtain this distance, then you must subtract 5 from the total distance, h1. Therefore, this distance is the distance h1 minus 5 centimeters. So let's move to our calculations. Notice that the pressure at the bottom is equal for both arms. So the very first thing to notice is that the pressure at the bottom is equal for both arms. In this left arm, we have the immiscible liquid and water. So we need to add the pressure due to the immiscible liquid, or the pressure in the immiscible liquid and the pressure in the water, and we equate it to the pressure in this section. So from the formula, pressure equals rho gh. So this is the formula for pressure in liquid. Rho ghi, where I is the immiscible liquid, I signifies immiscible liquid, plus rho gh of water through the height h1 minus 5, that is through this height, equals rho gh of water through the height h2. Remember that rho is the density, g is the acceleration due to gravity, and h is the height difference. So when you use the quantities that were given in the question for density and height and replace them in this equation, you obtain 4 times g times 5 plus 1 times g times h1 minus 5 equals 1 times g times h2. So at this level, remember that 4 is the density of the immiscible liquid, times g times 5, 5 is the height difference, plus 1, the density of water, times g into h1 minus 5. So it's this height difference must be equals to 1 times g times h2. So it's this other height difference. Effectively, g cancels out. So you need to observe there that g cancels out, and we are left with this equation 20 plus h1 minus 5 equals h2. We finally obtain h2 minus h1 to be equals to 15. I will call it equation 2. So remember that we first of all had an initial equation, and if we decide to solve these two equations either by substitution or by elimination method, we obtain h1 to be equals to 15 centimeters and h2 to be equals to 30 centimeters. Therefore, h2 and h1, that is the ratio of h2 to h1, is equals to 2. Hence, we conclude that the option C is correct. So now let us look at question 14, which reads, A thermodynamic process in which no heat enters or leaves the system is called A. Isothermal, B. Isochoric, C. Isobaric, and D. Adiabatic. So in this question, we are just going to look at the meanings of isothermal, isochoric, isobaric, and adiabatic. From there, you'll be able to pick the correct answer. So let us look at our solution. Isothermal processes are processes which occur at constant temperature. So from the word iso, which means constant, and from the word thermal, you can deduce temperature, and you can conclude that isothermal processes are processes that occur at constant temperature. So when we say a process is occurring at constant temperature, it means that when the process begins to occur, it may have a temperature of T initial to, let's say, 20 Kelvin, and when the process is ending, the final temperature is equal to the same 20 Kelvin. It therefore means that the change in temperature, which is equal to T final minus T initial, will be equal to 20 minus 20, which is equal to 0 Kelvin. So that is what we mean by an isothermal process, where the initial temperature is a particular value and the final temperature is still that same value. Therefore, the change in temperature is always equal to 0. So in an MCQ question, instead of writing isothermal process, they could say a process in which the temperature is constant, or they could tell you that a process in which the change in temperature is 0. So isochoric processes, note that isochoric processes are processes that occur at constant volume. And if the volume is constant, then the change in volume is also equal to 0 meter cube. Isobaric processes, on the other hand, are processes that occur at constant pressure. So when the pressure is constant, the change in pressure is also equal to 0 Pascal. So you should take note for adiabatic processes that they are processes that occur with no heat entering or leaving the system. Usually we write mathematically that the change in Q is always equal to 0 joules. So adiabatic processes are processes in which the change in heat energy is always equal to 0, or they are processes in which no heat enters or leaves the system. So now let us look at question 15, which reads, which of the following statements about thermal equilibrium is not correct? At thermal equilibrium, A. Heat flows from a hot to a cold object. B. Heat flows from a cold to a hot object. C. Heat flow ceases. And D. There is no net heat flow. Let us move straight into our solution. So thermal equilibrium is a very important concept in thermodynamics. And when two systems are said to be in thermal equilibrium, then it means that there is no net heat flow between them, or there is no net heat transfer between them. This occurs when the systems are at the same temperature. So when two systems attain the same temperature, the net heat flow between them is always equal to 0. And that is a condition, or that is what we mean by the two systems to be in thermal equilibrium. In other words, systems at the same temperature will be in thermal equilibrium with each other. So if you have a body at 1000 degrees Celsius and another body at 100 degrees Celsius connected to this body or at 1000 degrees Celsius, then there's always a two-directional heat flow between the two systems. But the amount of heat energy, or the rate of heat flow from the hotter object to the colder object, is usually higher than the rate of heat flow from the colder to the hotter object. And the net heat flow is equal to 780 joules per second. In this case, it's simply gotten by taking this quantity minus this. But a time arises where both objects are at the same temperature, and hence the rate of heat flow between the two is the same, and the net heat flow is equal to 0 joules per second. Hence the option is correct. So now let us look at question 16, which reads, the mean drift velocity of an electron in a copper wire having cross-sectional area 5.0 times 10 to the negative 6 meters squared, carrying current of 1 ampere, and having number density 8.5 times 10 to the power 26 meter cube is, we are given options A, B, C, and D. Let us move straight into our solution. So the area was equals to 5.0 times 10 to the negative 6 meters squared. I, the current, was equals to 1 ampere. The number density N was equal to 8.5 times 10 to the power 26 meter cube. From the formula, I equals NEVA, where N is the number density, E is the charge on an electron, V the drift velocity, and A the cross-sectional area of the copper wire. Making V subject of formula, we obtain I on NEA. So when we replace I by 1 ampere and all the other quantities in the denominator by their respective values, we are going to obtain V, that is the drift velocity, to be equal to 0.015 millimeter per second. and it corresponds to the option A. Observe here that a lot of analysis were made. So at this level, we obtained 1.47 times 10 to the negative 5 meter per second. And when we analyze that, that is by rounding up this value, we discover that this value is approximately equals to 1.5 times 10 to the negative 5 times 10 to the power 3. We're trying to convert it at this level to millimeters. So in converting this value, 1.47 times 10 to the negative 5 meter per second to millimeters, we obtain this value, which is equivalent to this value. We concluded that the option A is correct. So now let us move to question 17, which reads, the overhead high tension power lines from the Edea power station carry A. Alternating current at low voltage, B. Alternating current at high voltages, C. Direct current at low voltage, D. Direct current at high voltages. The very first thing to recognize here is that power stations do not produce direct current, hence C and D are wrong. These two options are already discarded. But power stations do produce alternating current, but these alternating currents are transmitted in power lines under very high voltages. And the reason for this is that these alternating currents are to be transmitted over very long distances, and so must be transmitted under high voltages to reduce power loss. So in high tension power lines, alternating current is transmitted in high voltages. So in high tension power lines, alternating currents are transmitted in high voltages, and this is done to reduce power loss. So this option is the correct option, but A is wrong because we cannot be transmitting alternating current in high tension power lines, which are essentially supposed to be transmitted over long distances, and we are doing so in low voltages. If we do that, then we are going to lose a lot of power before it reaches its destination. Hence, we conclude that the option B is correct. So this option is wrong, and this is your correct option. So now let us look at question 18, which reads, in a pure sample of silicon, A. The number of holes and free electrons is always equal. B. The number of free electrons is more than the number of holes. C. The number of free electrons and holes is equal at low temperature. D. The number of free electrons is less than the number of holes. So now let us look at the solution. We notice that semiconductors can be subdivided into intrinsic and extrinsic semiconductors. Intrinsic semiconductors are also known as pure semiconductors, and we notice that such semiconductors always have the same number of holes and electrons at any temperature. And we notice that such semiconductors always have the same number of holes and electrons at any temperature. While extrinsic semiconductors can be subdivided into N-type and P-type semiconductors. An N-type semiconductor is one which is obtained by doping an intrinsic semiconductor with a pentavalent element, while a P-type semiconductor is one which is obtained by doping an intrinsic semiconductor with a trivalent element. N-type semiconductors can be obtained by doping an intrinsic semiconductor with an element like phosphorus, while P-type semiconductors can be obtained by doping an intrinsic semiconductor with an element like boron. Essentially, N-type semiconductors are those extrinsic semiconductors in which majority charge carriers are electrons, while P-type semiconductors are those extrinsic semiconductors in which majority charge carriers are holes. So here we always have more electrons than holes, and here we always have more holes than electrons. So for N-type semiconductors, we always have more electrons than holes, and P-type semiconductors, we always have more holes than electrons. So here we say that electrons are majority charge carriers while holes are minority charge carriers, and at this level we say that holes are majority charge carriers while electrons are minority charge carriers. So with this information, we can conclude that the number of holes and free electrons is always equal. So this works for a pure or intrinsic. Remember that a pure semiconductor is also an intrinsic semiconductor. So let's read the option B. The number of free electrons is more than the number of holes. This only works for N-type semiconductors. So this only works for N-type semiconductors, and N-type semiconductors are extrinsic and not intrinsic, so this option is wrong. The number of free electrons and holes is equal at low temperatures. No, this is wrong because even as temperatures increase, the rate at which electrons will move from the valence to the conduction band will always be in such a way that the same number of holes will be formed. D. The number of free electrons is less than the number of holes. This only works for P-type. So this only works for P-type semiconductors. which is extrinsic. So this option is wrong. This option 2 is wrong. So now let us look at question 19, which reads, when temperature rises, the resistance of a negative temperature coefficient thermistor A increases, B decreases, C 0, D infinity. So let's look at the solution. In this question, we notice a term, temperature coefficient. So the full term is actually temperature coefficient of resistance, and it's a constant that is usually represented by alpha. Actually, the resistance of some materials increase as temperature increases, while for other materials the resistance decreases as temperature increases. And the constant that defines the change between the resistance and the temperature of a material or of different materials is known as the temperature coefficient of resistance. And it is defined by the formula change in resistance per unit change in temperature. So the constant alpha is known as the temperature coefficient of resistance and symbolizes the resistance change factor per degree of temperature change. So for pure metals, this coefficient is positive. So when alpha is positive, that is greater than 0, it means that the resistance increases with an increase in temperature. But for other elements such as carbon, silicon, and germanium, the coefficient is negative, that is less than 0, and it means that the resistance decreases with an increase in temperature. So a thermistor is a good example of a material in which the temperature coefficient of resistance is less than 0. Hence, the resistance, so when temperature is rising, the resistance of a thermistor will rather be decreasing. But when temperature is decreasing, the resistance will rather be increasing. So this is your correct option. The correct option here is B. A is wrong, C is wrong, and D is wrong. So this is the reason here. So you need to take note of this formula. Temperature coefficient of resistance alpha is defined as the change in resistance per unit initial resistance per unit change in temperature. So now let us look at question 20, which reads, which property of light is responsible for the formation of rainbows? A. Dispersion, B. Reflection, C. Refraction, and D. Diffraction. So we are going to look at the definitions of these terms, and we are going to look at those under our solution. But before looking at the definitions of dispersion, reflection, refraction, and diffraction, we should first of all remind ourselves of what a rainbow is. Actually, a rainbow is simply the 7 colors we usually see when the rain is falling and at the same time the sun is shining. So when rain is falling and sun is shining, we usually observe some 7 colors in the sky, and those 7 colors are usually called the rainbow. So dispersion is a process of white light splitting into its constituent colors. Reflection is a bouncing of light off a surface. Refraction is a bending of light as it moves from one medium to another, while diffraction is a bending of light around an obstacle. Already from the definition of dispersion, we can conclude that dispersion is the answer to this question, and that is actually correct. So when white light is split into its various colors, it forms a rainbow. And dispersion is a process that occurs in raindrops when the sun is shining during rainfall. So during rainfall, as the sun shines, the raindrops are usually seen to disperse light into its constituent colors, or they are usually seen to split light into its constituent colors. So remember that white light constitutes of 7 colors, and those 7 colors are given by the mnemonic Roy Beef. Richard of York gave battle in vain. So this is the mnemonic for you to be able to retain all the 7 colors of white light, where R stands for red, O stands for orange, Y stands for yellow, G stands for green, B stands for blue, I for indigo, and V for violet. So during sunshine and rainfall, so when the sun is shining and rain is falling simultaneously, and the sun is emitting white light that tends to hit the raindrops, so this is white light emitted from the sun and is hitting on the raindrops, then the process of dispersion occurs and the white light is seen to be split into the various colors, that is all of these 7 colors of light, and a rainbow is usually observed by an observer. So during sunshine and rainfall, so when the sun is shining and the rain is falling simultaneously, dispersion occurs in raindrops and a rainbow is usually observed. So that is how rainbows are formed basically. It's important to know that at this point, So at this point, the process of diffraction occurs. So at that point, we have diffraction. At this point and at this point, we have total internal reflection, and at this point, we also have diffraction. So at this point, we also have diffraction. But the actual splitting of light into its constituent colors is the process of dispersion, and it occurs in raindrops during sunshine. So we can conclude that the answer A is the correct option. Option B is not correct, option C is not correct, and option D2 is not correct.